carbonyl compounds, such as ketones, with an alpha hydrogen are actually acidic on this position because the conjugate base, which is the alpha carbonyl, is stabilized by resonance. Let's draw that scheme, reaction scheme again. So if this ketone is deprotonated at this position, an alpha carbonyl is formed, which is this one here. This is the alpha carbonyl. Now the alpha carbonyl can undergo resonance to form the corresponding enolate, as we have seen generally in a previous scheme. So resonance, stabilization of the alpha carbonyl can give the corresponding enolate, whose structure is this. So this is an enolate, therefore. That's an enolate. And remember, enolates are nucleophilic at oxygen and carbon. Of course, the nucleophilicity of carbon is higher because the C alkylation product is more favored thermodynamically than the O alkylation product, as we have described before. So this is the enolate. Obviously, this is the alpha carbonyl, and these conjugate bases of the general compound, the general carbonyl compound with an alpha hydrogen, is stabilized by resonance. And that's exactly why our carbonyl compounds with an alpha hydrogen are actually acidic. For ketones, as we have specified before, pK in general is about 20. So pKa here is about 20. So a good question would be, what base can do this deprotonation chemistry? So what base can convert ketones, for example, into the corresponding enolates? Now the base should be of an appropriate strength, and the condition is that the pKa of the conjugate acid of the base, which we should use in order to do this deprotonation, should have higher value or magnitude than 20. So let's take an example. So what are these substances with a pKa higher than 20? Well, you can think of amines, obviously. pKa, if you take ammonia, for example, okay, the pKa is 36. The pKa of amines in general is about 40. So let's draw the structure of amines. Therefore, this is general structure of amines. Okay, the pKa here is about 40. Recall again the pKa of ammonia, which is 36. So if you want to write ammonia, okay, pKa 36. Now, if amines lose that proton to a strong base, okay, then this conjugate base of the amine is actually formed. If that hydrogen is removed with a suitable base, then that conjugate base of an amine is formed. So this is called an amide ion. Now, if you compare the basicity of this amide ion with the basicity of the alpha carbonyl or the enolate, you would find out that the amide ion is actually a much stronger base. Now, this suggests that the weaker acid, we have the ketone, of course, whose pK is 20, and we have the amine, whose pK is 40. Between these two, obviously, the amine is the weaker acid. So the amine, we can describe it as weaker acid. The ketone is the stronger acid, and of course the alpha carbonyl or the enolate is therefore the weaker conjugate base. So this is the weaker conjugate base. The amide ion is the stronger conjugate base. So if we react the stronger acid, which is the ketone, with the stronger conjugate base, which is the amide ion, this acid-base reaction can take place. So therefore, a suitable base that can deprotonate carbonyl compounds, in this case ketones, with an alpha hydrogen should be an amide. So NR2 in general, an amide ion, is a suitable base for the deprotonation of ketones at the alpha position to make alpha carbanions, and therefore enolates. This is all due to the pKa, therefore it's all due to the acid strength. The stronger acid should react with the stronger conjugate base, but not vice versa. Now amide ions can be made from amines by reacting amines with very strong bases, and typically those are organolithiums, RLI. RLI is a general formula for organolithiums. Organolithiums can deprotonate amines to make the corresponding amides. Of course, if you take the conjugate base of ammonia and H2 minus, the simplest amide ion, that's good enough also to deprotonate ketones or carbonyl compounds at the alpha position. So the suitable base, therefore, should come from an acid whose pKa higher than 20. So this is the base that's required. This is the acid. The pKa here, it should always be, if that acid is desired to deprotonate carbonyl compound, the pKa here should always be higher than 20. So this is the requirement, if you like. Any base which comes from an acid whose pKa higher than 20 can deprotonate ketones at the alpha position. So amide ions in general are the suitable bases to deprotonate ketones and other carbonyl compounds of a similar pKa or even higher, slightly higher pKa. Amide ions can deprotonate such compounds at the alpha position to make the corresponding alpha carbanion or enolates. We have just learned that amide ions are the suitable bases to deprotonate carbonyl compounds such as ketones at the alpha position to make the corresponding alpha carbanion or enolates. Let's take an example of an amide ion. If you take isopropyl amine, remember the pK of amines in general is about 40, so the pK here is about 40, it's 38 actually, 38. If diisopropyl amine is deprotonated with N-butyl lithium, an alkyl lithium, which is a very strong base, this strong base can take off that hydrogen to make the corresponding amide, which is this one here. So it's diisopropyl. This is diisopropyl amine. That's diisopropyl amide. Of course, there is lithium here as a counter ion. This can also be drawn like this, where there is a covalent bond between lithium and nitrogen. So this is another possibility. Now, this is called lithium diisopropyl amide. Now, there are isopropyl groups on the original amine. Then the amide has two isopropyl groups. It's an amide now, but it's an amide that's bonded to lithium as a counter ion. So the name of this is therefore lithium diisopropyl amide. Lithium diisopropyl amide. This is abbreviated as LDA. LDA, L comes from lithium, D for diisopropyl, and A for amide. So the name of this amide base is LDA, and the typical base for this, for the deprotonation of carbonyl compounds, such as ketones, for example, is LDA. So that's the structure of LDA. It's an amide base, of course, which is formed if diisopropyl amine is deprotonated with a strong organolithium such as N-butyl lithium. LDA is a very commonly used base to deprotonate ketones at the alpha position to make the corresponding enolates.